Enols and enolates today. Second stream for the day. Let me upload my or refresh my channel, see if I can get a link. Is it not starting? Let me see. Oh, is it not starting? Nope, it started. All right, so we are now live again. Let me just post the link in the Discord. Hang on, we got a guest. You got a guest. Hi, Tristan. You gonna come hang out? You want to sit on the chair? Here, sit on the chair so they can see you better. I'm waiting a second for them to get logged in anyway. All right, sit. All right. Whoa. Let me know in the Discord if you guys can see me. Yeah, and as per usual, if you're watching this after the fact, I will be commenting on the start time of the lecture after the video goes to actual video. Do you guys see this cool shirt? Is he not a chemistry person's son or what? Yeah, so it's the periodic table of school. It's got scissors, glue, calculator, computer, stapler, compass, pens. Is that pants? No, paints. Math, reading, gym, music. I love it. All right, guys. So today's discussion is we are going to go ahead and talk about enolates today. So let me just move my keyboard out of the way because I'm not using the keyboard at all with this part. And if the boy wants to hang out, he can. Watch me teach. Yes, pants are necessary for school. I'm already thinking of like reoccurring nightmare people have where they have the dream that they're at school naked. Yes, pants are necessary. All right, guys. So today we're going to go ahead and I'm going to go ahead and officially start now. We're going to be talking about enols and enolates. I'm just doing the introduction today. Please don't do that, please. We're going to do enols and enolates today, and then basically just do the intro for it, and then I will deep dive next time. So we're going to do like a whole 80-minute lecture next time on the rest of the chapter. I just want to get the intro for you guys today. It says my son never wears them. Talking about pants. So he likes to run around naked too, I guess, sometimes. Am I embarrassing you yet? Just a little?
Sometimes I get too hot and I just take off my shirt.
Just your shirt? You run around in your underwear sometimes too.
Yes.
Yeah. I think it's part of being a kid.
Daddy does that sometimes too.
Whoa!
Especially when he goes to bed.
Okay, that's enough, Tristan. All right. I think I'm more embarrassed now than he was. All right, guys. So today we're gonna go over enols and enolates. I'm not gonna stop laughing now for this whole lecture. He got me the laugh bug in my brain now. All right, enols and enolates. Before we can go very far in this, I did want to go over keto and enol tautomerism. I think I showed you something really brief last time. But I do want to mention here that we have so-called keto enol tautomerism. Like so. So what happens here is we have a ketone. It could be an aldehyde too. He's hanging out my stream. Can become that. So we call this the keto form, and even if it's an aldehyde, we still call it a keto form. And here we have our enol. You guys may remember back when we were doing IR stuff back in Chemistry 241, I mentioned for you guys to never draw a OH directly on an alkene. for doing the IR stuff, and the reason why is because they actually favor this form. So if you were to draw a compound like this, they will tend to tautomerize that way. It works out that this is about 1%. It's in that form. There are some exceptions to this, though. One example here is this. It turns out that phenol is actually technically an enol, and then this can tautomerize to this. And I want to make sure that you guys are clear what the word tautomer means. Tautomer means they differ by the movement of one atom. So they're not quite resonance structures because something moved. They differ by one atom. We get that. So here we have our enol form. Here we have the keto form. So I'm going to get the question here. Out of these two, which one would you expect to dominate for phenol? Would the enol form dominate, or would the keto form dominate? What do you guys think? Anybody? Yeah, it turns out that this is actually an exception to the rule, and the reason why is due to aromaticity. So this particular compound is aromatic, this one is non-aromatic, so this one will be favored. So it works out where in this case here, this is probably less than 1%. And the explanation for this is that this one is aromatic, and this one is non-aromatic. And if you remember your aromaticity rules here, we have an sp3 carbon here with 2 H's on it. We can't push resonance through that. This is no longer flat. We no longer have a continuous pi system. This side is favored. All right, so I want to quickly go over the mechanism for this. I think I showed you guys something a few lectures ago on this particular one. So let's just go ahead and take a look at acetone. This is a concerted mechanism. I'm going to go ahead and draw all the H's out, like that. And then I want to make sure that you guys are all understanding that this carbon here is the alpha carbon. So the reason why I actually put this off here is because I like to think this is alpha carbon chemistry, so I don't like doing this during the aldehyde and ketone chapter. So what we can show happening is this can jump over, this can grab that, this can go like that, and then I like to kind of think of it as a intramolecular E2. You can think of it that way. But just so you're clear about what's happening here is this is becoming a single bond to O. This oxygen now is bonded to H. The carbon H bond is broken, and we now have a double bond here, like that. So we now have our enol, like that. The main reason why I don't introduce this stuff back during the aldehyde and ketone chapter is just due to the fact that we were going over these guys being electrophiles. But what we're going to see in this chapter, enols and enolates are nucleophiles. So you spent all that time learning all those different rules about these being electrophiles, but now we're going to flip it, and we're going to make them nucleophiles now. So fun times. The last thing I want to show you guys here is depending on if there's additional resonance structures, the enol form will become more apparent. So the example I have here is a beta diketone or beta carbonyl. So this is a beta dicarbonyl. These form enols readily. Form enols readily. So I'm going to go ahead and draw. So if you think about it here, we can form an enol to either one of these carbonyls, and these are all going to be in equilibrium with each other. This particular one just happened to be symmetrical. We're going to be working with these compounds a little bit in this chapter, and you're not going to unsee this, but this is totally Jar Jar Binks, right? From Star Wars, this Jar Jar, those are his eyes. But yeah, I can't unsee it now. Anyway, this is roughly 24% of this equilibrium. So it's significantly heavy on the enol side, just due to the fact we have 2 carbonyls potentially to do that with. All right. So moving along here, I did want to go over some of the acid-base chemistry here, and then we will go ahead and do some actual chemistry, or more traditional O-chem for that matter. All right, so let's go ahead and take a look at this particular ketone. And I am talking about specifically this H here. The pKa of these is roughly 19 to 20. Is approximately equal, that's my approximate symbol there, approximately equal to 19 to 20. So I'm going to go ahead and show the Ka reaction for this. When I say the Ka reaction, I mean that we're just deprotonating here, like that, and then we have the negative. You can then draw resonance of this anion. So the resonance here is going to basically be getting the double bond, and then this moves up. So let's use red for arrows today, like that. There is your resonance. And we have this. So we get that. So this is an enolate. So if you have the OH on there, you call it enol. If you have the O-, it's an enolate. So this is resonance stabilized nucleophile. Resonance stabilized nucleophile. These are going to be nucleophilic. So the general thing we're going to see in this chapter, there is a there was a question in the chat, could you please let us know which chapter you're on? So the thing is, I don't follow any particular book, but the thing is, each OChem book out there has the same kind of chapter. So there should be an alpha carbon or enolate chapter in whatever book you're following. My notes come from Solomon and McMurray, are the 2 books that I use to write my notes. That and a little bit from Klein. So it all depends on which book you're using, guys. I don't actually have a book for my class. So yeah, just use the index. I'm sorry, I can't give any more details than that. All right, so I want to show you 2 different ways that you can draw the arrows here. So what you're going to do is you're going to be reacting with some kind of electrophile. One way is to show the arrow coming straight from the lone pair, or you can show the arrow coming from the double bond, but you have to have an extra arrow push here. So we can show it that way, or you can show this going out to grab, let me make the arrow a little better, attacking an electrophile, like that. Okay, are there any questions so far about enolates? Any questions at all? No. Oh, someone's typing. Let me get the next page set up. So the next thing I want to go over here is racemization of alpha carbons. Would it deprotonate the left carbon? Yeah, so the question was, would it deprotonate the left carbon? I actually have a discussion about that after this topic. So we're going to go over exactly that on the next page. So hang in there. We're going to go over it. There is a way to choose which one deprotonates. All right, so let's take a look. So I'm going to go ahead and draw a particular enolate here. So what happens here is we have a chiral center, and the chiral center is going to go ahead and go right there in the alpha carbon. And I'm going to draw it as a dash wedge here, like that. Like so. And then we're going to go ahead and react this with NaOH, sodium hydroxide, like that. And then what is our product going to be? The way you want to draw this deprotonation, the arrow push looks just like an E2. So remember E2, we grab the H, like that, and then you get a new double bond, like that. In the E2, the leaving group leaves here. So I'm going to call it an E2 in quotes because it's technically not an E2, but the arrows are the same. So it looks just like an E2. All right, so then what we get from this is our enolate. Looks like that. All right, so before we move on to the next part of the reaction, I did have a question for you guys. So I just mentioned in the last page here that the pKa of this is about 19. And then the pKa of water is exactly 15.7. So the question I have for you guys is which side of the equilibrium dominates? This is from Chemistry 241. Which side of equilibrium dominates? Yep, the first response was correct. The reactants are going to dominate. The reason why is because equilibrium tends to favor the side that has the weaker acid and weaker base. And then it works out where going over this way, this is the weaker acid of the two. So we're comparing this acid versus this one. This is your weaker acid. This side dominates. So this side, so the thing is though that the pKa's are not different by a lot. That's not a huge difference there. So you're going to have an appreciable amount of both in solution. So we actually can use hydroxide to make enolates. Excuse me. If you actually look at the aldol experiment, we were supposed to do the aldol experiment, and I think it was like next week after spring break, I believe, remember right? But in that particular lab, we are making an enolate with hydroxide. So you do have the possibility of getting an addition product here, but if you have an electrophile around also, you don't just get the addition product, you also get the alpha carbon chemistry also. But I'm getting ahead of myself here. But for now, just remember, this side does dominate, but there is a nice amount of both here, so the reaction is going to go. Anyway, I'm going to redraw this a little bit. I'm just going to basically draw out the OH bond for the next step here. So what can happen now is this can act as a nucleophile, or sorry, a base in this case, and go out and grab an H from water. Like that. Remember, it's in equilibrium, right? So it can go back and forth. So the thing is, though, when it goes back, you get both products here. You get both the R and the S products here when it goes back. So we're going to get this one back. This is the starting one. And then we're also going to get the enantiomer. Like that. The explanation for this is that this portion of the molecule is sp2 hybridized. So I'm going to point there. This is an sp2 carbon. And if you remember the shape on these guys are trigonal planar. So what happens here is that when it goes out and grabs the H, and that the H can be adding on the top side or the bottom side because it's flat, right? So you end up with the racemic product. Racemic product. Therefore, we racemized the alpha carbon. All right, are there any questions about this here? Any questions at all? All right. So I did want to go over this next portion here. Yeah, I want to do 2 more little pages worth of stuff, and then I think we're going to be done for today. So this is, I think I see someone talking. Just go ahead and type out your question. I'll see it. All right, so I'm going to go ahead and give a definition here. So next section here is going to be regioselectivity of enolates. I thought I saw someone typing. I guess not. All right, so well, all of these reactions require an acid or base catalyst. Not always. Often. Oftentimes in this chapter, you're going to have to form an enolate first with the base. We will very often use a base for this to get it started. All right, so I'm not sure if you guys learned this word in 241. I know I teach this word in 241. So I'll just go ahead and give you the definition here for those that didn't learn this. This word right here. What regioselectivity means is that you're getting one constitutional isomer product. So if a reaction is regioselective, you get one constitutional isomer product. So the kind of things that we were thinking of here is like Zaystad versus Hoffman, Markovnikov versus anti-Markovnikov. Those kinds of reactions are referred to as being regioselective. Where a reaction like addition of H2, that's symmetrical, that's not regioselective, that kind of thing. And then if you're getting one enantiomer, the word we use is stereoselective. So once again here, regioselectivity is referring to basically getting the enolate on one side or the other, is what we're talking about here. All right, so I'm going to go ahead and start here with an asymmetric ketone, like that. We're going to have 2 possibilities here. One of them is going to form the enolate on the left side. One of them is going to form the enolate on the right side. So we're kind of reviewing a little bit of E2 chemistry here, back from last semester. So the main difference here is going to be the use of a small or a bulky base. Which one do you think the bulky base is going to make? So a bulky base, I think it was LDA or things like potassium tributoxide, the big bulky bases. Which one do you think is going to form with the bulky base? Yep, that's exactly right. The bottom one is going to form. The reagent here is LDA. For those of you guys that did not have me for 241, I introduced this reagent during the E2 chapter for the Hoffman elimination, the less substituted products. This is a bulky base. So we have a bulky base, and don't worry, I'll draw it out here in the bottom here in a second. And then up here we can use something like NaOH or Na or Naomi. Yep. I call that one Naomi. Don't judge me. But here on the top, we have a small base. So the reason why this happens this way is because this is actually the more favored product thermodynamically. So more stable carbon-carbon. This one is the less stable. Remember, for alkene stability, the more substituted it is, the more stable it is. So more carbon groups coming off. You could think of it kind of like the difference between thermo and kinetic products back when we did the diene stuff. So this one, while it's more stable, it's it's easier for this to get in here and grab that, where this one here is the bulky group is too big to get inside of there to get that H, to get to that other product. So this one goes on the outside instead. So bulky base is too large to get to the H. That gives more stable enolate. You're going to have to, oftentimes in this chapter, you're going to have to make decisions on which side you want the enolate to form on, and this is how you're going to distinguish between them. So if you want it on the more substituted side like this, you want to go ahead and use the small base here. And then if you want it to be less substituted on the right side, for this example, you want to use the bulky base like LDA. All right. So I had a thing here in my notes. Where is it? Where is it? Hang on, I had another thing here I wanted to talk about real quick with this stuff. Where did I put it in my notes? There we go. All right, so let's go ahead and take a look at the chemistry that's happening here. So here I have a ketone. I'm going to show it reacting with LDA. I'm actually going to draw out LDA now. So LDA stands for lithium diisopropylamide. And I'll write that name out too. So we got that. And then our lithium is out here as the counter ion for it. We're going to have some equilibrium here. And then we're going to have that. And then, so here if I have the base, I need to draw the conjugate acid. The conjugate acid has an extra proton on it, and it's now neutral. Lithium goes here. So let me write this stuff out up here. So it's lithium diisopropylamide, or we call it LDA for short. So here is your LDA, like that. And then over here we have our enolate. The other comment I want to make here is that LDA is not a nucleophile. Can anybody explain to me why LDA is not nucleophilic? So not a nucleophile. Does anybody want to help me explain why this compound is not nucleophilic? You want to think back to SN2 from last semester. Nobody? Okay. So the short version of the reason why it's not nucleophilic is the fact that it's too bulky to be a nucleophile. So it is easier for it to act as a base instead because of how it's all to the size. So size does matter, right? All right. So another thing I want to mention here too before we move on is I had pKa's here. So the pKa of this one was about 19. The pKa for this one is 38. Which side of the equilibrium dominates? You have to answer that one. Which side dominates in equilibrium? See people typing. Yep, the right side dominates. That's the weaker side. So oftentimes these amide bases are very strong. Strong bases, they are great for this kind of chemistry. If you want this chemistry to occur. All right, so I have 2 more reactions to show you guys. I'm going to go over one in a little bit more detail, but I'll show you guys some stuff we can do. So it turns out that we can alkylate the alpha carbon. So the next reaction here is alkylation of the alpha carbon. If you've forgotten what the word alkylation means a new carbon-carbon bond. So this word right here means a new CC bond in your compound. So what I'm going to go ahead and do here is we're going to form an enolate from acetone. And I just want to show the mechanism for all this too. So we drop these H's. Let's go ahead and say it was LDA. The negative charge on it's going to grab this H. Like that. Oh, before I continue, I want to mention some people like showing this part is what they'll do first is they'll do a tautomerism with the keto enol and then grab the H off the OH. I guess technically it's right, but I prefer it this way. Show it as an E2. All right. So we get this. Like that. So earlier I showed you guys that these things can then go out and grab electrophiles because this is nucleophilic. So this is the nucleophile. And the example I'm going to use is this. Like that. And then what we do is you reform the carbonyl. This can go out and grab and do that. You guys recognize this at all? Like so. Just ignore this whole enol stuff and like nucleophile, what is that? What kind of reaction is that? Ignoring the enolate for now. So nucleophile comes in, does a backside attack. What is that? Anybody? What kind of reaction is that I just showed? It has a name. Yep, that is SN2. Yep. So I'm not sure if you guys can tell yet or not what we're doing basically. So what we're going to be doing now is we're going to be revisiting all these old reactions, but we have a crazy nucleophile now. So we're going to go back through SN2. We're going to do acyl substitutions. We're going to basically revisit all these old reactions with the new type of nucleophile. There is some actual new stuff in this chapter though, but on these kind of problems, you have to be very careful on your carbon counting. It's really easy to lose count of carbons. So we have this right here, new bond right there. So we have 2 new carbons. We get that now, like so. We got good call, guys, on drawing your SN2 with that. All right, trying to see something else I want to do with this one. All right, so one thing I want to something else I want to show you guys here, and I think we're going to go ahead and end with this here. Hang on, let me find it in my notes. I lost where I was at. One moment, please. Yeah, so I want to mention also that if you guys are looking at my notes, I actually do the HBZ reaction in this chapter. Hannah did it last chapter, so all right. So the next thing I want to show you guys here too is that we actually can halogenate these. So I'm going to call this one the let me start a new page here. I need more room. So the next thing I want to go over is the haloform reaction. Like so. And I am going to specifically start with a methyl ketone again, or acetone to be my example for all these. That, and we're going to have some equilibria here. So the base I'm going to use in my example here is NaOH. And this is going to deprotonate. It's going to act as the base in an E2-like mechanism. Oh, something else I want to touch on too here before I continue. You may recall from last semester when I was going over like SN2 versus E2, I would say things like hydroxide acting as a nucleophile, hydroxide acting as a base. It's the same kind of thing here. So if you have the addition reaction happening, hydroxide acting as a nucleophile, if you're getting the enolate, hydroxide acting as a base. So the same kind of terminology is exactly the same here instead, or the same thing as we saw last semester. All right, so here, what I'm going to show happen next for the haloform reaction is we are going to react this with X2. So XX. So this can be something like Br2, I2, Cl2, etc. is what's happening here. And what will happen here is reform that. Go out and grab one of these. Remember, these guys are electrophilic. We saw that in the alkene chapter last semester. And then what we have is this. So here we call this the mono-alpha halogenation. But I'm going to add a little comment here. With 1 mole equivalent of X2, you get the monohalogenation of this compound. So the question was, are there cases where we need to use our X based on the strength of the halogen? I don't think so. If I'm understanding your question correctly, I don't think so. All right, so once again back here with 1 mole equivalent of X2, you get monohalogenation of the alpha carbon. The reaction will continue if you have excess X2. So reaction continues with excess X2. Remember, that means excess, we have a lot of extra of it. So backpedaling here a second here. We started with this. We're going to have X2 and NaOH. Like that. This can happen again. Same exact so the same mechanism for every step, guys. So it's all the same for each step. It's just happening over and over. Okay. In the case, if you have a methyl ketone like we have here, the reaction happens one more time. It's going to happen for every H. So once per H on alpha carbon. So because we have a methyl group there, we can do it one more time. Like that. We get that. And because OChem, we're not done yet. So it hang on, I got a question. It's not quite the same as the alkene reaction. So the question was, would it go bromination of an alkene mechanism? It's not quite the same. We're only going to get one bromine on the alpha carbon in this case. You don't get bromine adding onto the carbonyl carbon. If you're comparing it straight to an alkene, it doesn't do that. All right, so at this point here, we have 3 of these halogens on here. It turns out what happens here is that this is now a leaving group. So at this point here, this is now a leaving group. So what can happen is an acyl substitution, which last chapter stuff. So I'm going to show that down here. So I'm going to shorthand this as CX3 for short. And we still have hydroxide around. This can do a nucleophilic attack on the carbon, like that. We then get a tetrahedral intermediate, CX3OH, and because we have a leaving group now, we can reform the carbonyl, knock out the leaving group. Running out of room here. Thankfully, we're almost done with this mechanism. Otherwise, I would be in trouble. Almost out of room. All right, and then the last step here is you want to show the leaving group here, grabbing the extra H because we are in basic conditions. You could also show hydroxide doing this, but I recommend using the halogen group to do this because of the final products. So we get carboxylate, and you get a haloform. CHX3 is a haloform. So for example, chloroform is CHCl3 is chloroform. All right. So I want to add another comment on here before we end it, is that this is a qualitative test for methyl ketones. So remember last semester we did in lab we did the bromine test for double bonds. This is kind of that kind of test for a methyl ketone. They all end up being positive here, and we'll see the haloform in solution typically. I think they use iodine. Remember right? I don't know if the other professor here wants to help out. I believe it's done with iodine. I don't remember. I think it's iodine for the qualitative test. Let's see if he'll type. Anyway, do you guys have any questions about the haloform reaction? Any questions at all? God, it's so beautiful outside right now. Oh my God, it's so nice outside. I want to go to the park. Yes, iodoforms. Yeah, they use iodine for this. That's what I thought. Okay, I want to show you guys. So we are actually going to end this soon. I think this is actually a good stopping point, but I want to show you what's coming. If you want to look ahead, we got some pretty fun stuff coming up. You know what? You guys know what stuff I think is fun. Yeah, bright yellow precipitate is the other professor is saying. So let me go ahead and show you what's coming. This stuff is, in my opinion, the hardest part of the semester for most students. So be ready. So let me switch over to the file view, give you guys a heads up what's coming. Let me zoom in. So these are my lecture notes I have posted online, guys. Oops. So we're going to be going over this acedoacetic ester synthesis. What's happening here? We're basically applying a couple different reactions all in one reaction here. So the first step here does a deprotonation, giving us an enolate. We can then do an SN2 with an alkyl halide, and then at this point we can then do a saponification to get rid of the ester group. And then you notice here now we have a beta keto acid which can decarboxylate. So we now have an alternate way to make methyl ketones. And whatever is coming off of the alpha carbon is whatever the R group was on your alkyl halide in the first step over here. So that's one thing we're going to be going over next time. I asked you guys to try this on your own. During that last lecture, or it was 2 lectures ago now, I think, I asked you to try the mechanism for decarboxylation. It's right here in the notes. I am hoping for tomorrow about the quiz. Another thing here too, I'm going to go over acylations here. So we're going to be doing acylations with this alpha carbon stuff here. So basically we have this crazy nucleophile undergoing an acyl substitution. So I know this looks confusing, but please bear with me. You guys know this. This is an acyl substitution. We did this last chapter. This is no problem for you guys now. Anyway, after the acyl substitution, we then undergo a saponification, like that, and then this next part here decarboxylates to a beta dicarbonyl ketone. Jar jar. The question was, what is DME? It's dimethylglyoxime, I believe. Yeah, it's a solvent. I wouldn't worry too much about it. It's a solvent. I'll look it up, make sure I have the correct structure for the solvent next time. Anyway, moving along here. So next we'll be going over malonic ester synthesis. This is the same kind of thing, except now we have basically 2 carboxylic acids, and one of them will eliminate via decarboxylation. And then we have a fun practice problem here that I worked through, that we make isoleucine, which is one of the amino acids. We make that from the malonic ester synthesis. It's all here in the notes if you guys want to look ahead. All right, so the next thing here, real quick, Claisen condensation. This is another example of an enolate doing an acyl substitution. It's a special case. It's ester and ester reacting together. The Deichmann condensation is basically an intramolecular version of it. And I want to show you we have to do the aldol reaction as well, the aldol reaction. And then we are going to be doing the Michael addition, simple versus conjugate. So I'm hoping to get this all done in one lecture, guys, next time. We should be able to do that. Yes, esters can be hydrolyzed under acidic conditions, but it's usually done in base. But you can show a mechanism with that. So I apologize. This last page of notes here didn't scan very well, but I know what it says, so I'll just write it out when we go over it. But I know what this says. So bear with me, guys. You guys can do this. Hang in there. All right. So let me switch over to face cam. I think we're at a good stopping point. We've also actually gone over like 90 minutes already, or almost 100 minutes now. So I think that's enough OChem for the day. So as for you guys, stay safe, hang in there, stay at home, be healthy. Don't forget to work out a little bit. And I'll be in the Discord chat as usual, and to hang out if you have questions. So stay cool.